current question is S gives A gives A or B. These are the productions. We have to construct a CLR parsing table from the given productions. So considering this, first we have to write the augmented production for grammar, which includes an extra production S dash gives dot S, comma dollar. Here dollar is the augmented for the augmented production. And after getting this, we have to number each of these. So we get 1, 2, 3. After numbering this, we have to find the lookaheads for all of this. To perform lookahead operation, we have to consider the three below cases. Since the above problem, the above productions satisfy only this rule, we find first of beta. That is, here we find first of A, that gives A or P. Since these are the lookaheads for these two, second for the productions 2 and 3. Since these given initial productions, we consider them as initial state I naught. From that, we have to read S, A, small a and small b. After reading this each, we get the point to the right side of this, like this S. Since it is the left side, after reading S, we will get it to the left side. Similarly, we do it with capital A and small b. Since at I2, it is not at the furthermost right side, we have to find other states for I2, which is I5, states I5, I6 and others. Here we see that a point is at the rightmost, so we need not shift it further. Since we got it here, we have to check for other things like a.a.a. Since we have to do for these both, we do like this, and we get states I7, I8 and I9. Considering these, which are at the farthermost right, we need not solve this problem much further. Remember this reduced. These are the final reduced values we got for the above initial production. So let us draw the CLR partial table from the previous derived state. So we have 10 states here, starting from the initial state 0 and ending at the final state 9. Since here reducing from initial state for A, it is finally reduced at 3. So we write its value at S3. It is shifted at S3. So we write it at S3. Similarly, with the case of B, we got it at 4. So we write it at 4. This is the same for all the shift cases. Coming to reduced cases, consider this 8 and 9 for suppose. We have 8A, 8B as R2, R2. Since we got the final reduced production here in I8, we included 8 here for AB. So since the numbering for this production is given in the beginning of this question as 2, we write it R2. Similarly, with 7 and 5, we give the respective numbers. Now the topic is dead code elimination. In compiler theory, dead code elimination is a compiler optimization to remove code which does not affect the program results. It has two benefits. It shrinks the program size and it allows running program to avoid executing irrelevant operations, which reduces its running time. Dead code includes code that can never be executed and code that only affects state variables that is irrelevant for the program. Considering the given example, in the given example, we have the program like this. Here, even though we write the values like I equal to 1, global 1, global 2, global 3, global 3, we do not print the values I equal to 1, and after the return, we do not implement global equal to 3. So this is a dead store problem. Eliminating the dead store, after eliminating the dead code elimination, we get the problem like this. Now, copy propagation. In compiler theory, copy propagation is the process of replacing the occurrences of targets of direct assignments with their values. A direct assignment is an instruction of the form x equal to y, which simply assigns the value of y to x. From the code, we can understand what is copy propagation. Copy propagation often makes use of reaching definitions, use definite chains, use chains when computing which occurrences of the target may be safely replaced. If all the upwards exposed uses of the target may be safely modified, the assignment operation may be eliminated. Copy propagation is a useful cleanup optimization frequently used after other optimizations have already been done. Some optimizations such as elimination of common subexpressions require that copy propagation be done afterwards in order to achieve an increase in efficiency. Considering the code motion in computer programming, it is also code motion also called loop variant code. It consists of statements or expressions which can be moved outside the body of a loop without affecting the semantics of the program. Loop invariant motion is a compiler optimization which performs this movement automatically. Considering the example here, we do not need the values 6 star I plus x star x and x equal to y plus z. These two expressions are not needed. Keeping them out of the loop, we get the result like this.